Hello and welcome. Today we're going to have a look at how to do rectangular to polar conversion on a Casio FX82. So why would you want to do this? Well, let's have a look and show you the benefits of being able to do these sorts of conversions on this calculator. We all know that everyone loves phasor diagrams, and we would normally use a phasor diagram to solve a question like this following one. Determine the supply current and phase angle for a 230 volt 50 Hz parallel AC circuit where the resistive branch current is 5 amps at 0 degrees, that's in phase with the supply voltage, and the inductive branch current is 5 amps at minus 60 degrees, that's lagging the reference, which is the supply voltage, by 60 degrees. Now normally to do this we would draw a phasor diagram. So here we have a template that we can draw our phasor on. We're going to use a scale of 10 millimeters equals 0.5 amps. So let's draw our reference phasor in. Now the reference phasor would be the supply voltage, and the resistive current is in phase with the reference, the supply voltage. So we draw the resistive current in to scale, and we have 5 amps there, and you can see it's at 0 degrees right here. Now we draw the inductive branch current in, and that's lagging the reference by 60 degrees, so we draw it 60 degrees in the negative quadrant. You can see the angle here, 60 degrees, and based on the same scale, 10 millimeters, we've drawn it 5 amps in length. It's exactly the same length as the resistive current, and there's the 60 degrees between the two. So normally we want to find what the total of those two are, so we do a phasor addition to do that. So we draw in the construction lines, and then we find the result, which is the green line. So if we then measure that green line, you can see the length of it, and if we use our scale 10 millimeters equals 0.5 amps, then we come up with a total value of 8.8 amps, and you can see that the angle of the result here is about 30 degrees. So the 5 amps in phase with the reference, the 5 amps 60 degrees lagging the reference, sum together to give us 8.8 amps 30 degrees behind the reference. So there's a phasor diagram to actually solve that question. Okay, so that's how you would normally do it. Let's show you how we can actually do that by using a calculator instead of the phasor diagram. So here's our Casio FX82. You can use other calculators, but this is the particular one that we prefer to use. And now on this calculator, it's got a polar to rectangular converter. So you can either go polar to rectangular, or you can go rectangular to polar. You can convert either way. Polar coordinates are the coordinates, or it's a way of describing a point with a length or a magnitude and an angle from the reference. And you can see those values that we talked earlier, the 5 amps at 0 degrees and the 5 amps at minus 60 degrees. They are polar coordinates. So we know how long it is, and we know what angle it is, which defines that point. You can also define the same point using rectangular coordinates. That's where there's a certain x component to it and a certain y component, and if you plot the x and the y component, you can plot the same point. So here we have magnitude or value and angle. Here we have an x value and a y value. That's a rectangular coordinate, that's a polar coordinate. So what we need to do to solve this, we need to convert the two polar values into rectangular values. So we convert from polar to rectangular, so we get the x and y component for our two values, the two currents. Then we add those together, just mathematically, and then we take the result and we convert it back to polar, which gives us an answer. So we have two polar coordinates, we find the rectangular values for those, we add those together, and then we convert those back to polar to get the answer. So here's how we do it. This is out of the calculator's instruction manual. This shows you the keys to press along here to actually get the answer. So that would be the keystroke function to get the x and y components for the first current, that's the resistive current, which is 5 amps at 0 degrees. This would be the key structure to go through to get the x and y values for the second current, which was the inductive current, 5 amps at minus 60 degrees. And if you follow on along with the calculator, you can see how you actually press the key strokes to get this to do its thing. So we press shift, then we press, the reason we press shift is we want second function. That gives us the rectangular. So we're going to put some polar values in and get a rectangular answer back. So you can see here it's 5 amps. We press shift and then the right bracket, which gives us a comma. Then we press 0. There's your 5 amps at 0 degrees. Then you press the bracket to close that off. Then we press the equals, and that gives us the x and the y values, the rectangular components of our polar coordinate. So we have 5 amps at 0 degrees, which gives us an x value of 5 and a y value of 0. Now we'll do the second one, the inductive current. We write those two down here. We need those later. So we go back to shift. We press the negative or the minus button, which gives us second function rectangular. This time we've got 5 amps and minus 60 degrees. So we need the 5, and then we need the comma, which is second function right bracket. Then we need the negative sign because it's minus 60. Press the 6, press the 0, and then press the close brackets. Then we can press the equals button to get the answer. And for the inductive current, which has 5 amps at minus 60 degrees, we get an x component of 2.5 and a y component of minus 4.33. So there you can see the two processes to get the x and the y value for both of those currents. So we've converted 5 and 0 polar to x5, y0. We've converted 5 minus 60 degrees polar to x 2.5 and y minus 4.33. Okay, and there's the mathematics now to actually get the total. So we need to add those together to get the result. X equals 5 plus 2.5, which gives us a grand total of 7.5 for the x component for our answer. The y was 0, and then 4 minus 4.33, which gives us minus 4.33 for our y value. So you can see here, the 5 and the 0 is the resistive current. The 2.5 and the minus 4.33 is the inductive current. That when we add those two together, we get a total of 7.5 and minus 4.33. These are the two down the bottom here. They're the values we're going to put into our calculator now so that we can convert them back to polar, which will give us the length of the supply current, or the value of the supply current, and the angle as well. This is the process here that we need to go through to do that. So these are the keystrokes from the calculator instruction manual to convert 7.5 x value minus 4.33 y value to convert that to a length and an angle. So if you have a look at the calculator, we'll show you how you do it. So we press shift for second function and the plus, because this time we are putting in rectangular coordinates and getting a polar answer. So the first one is 7.5, so we press those, and we press shift right bracket, which gives us a comma. We put the negative in because it's minus 4.33, so we press the 4.33, and then we press the right bracket to close it off. And now we've got our answer by pressing equals, and you can see here that the answer is 8.66. That's the length or the magnitude of the result, and the angle is minus 29.999. We've got them over here, so that's the actual keystrokes to convert those rectangular coordinates to the polar, the length and the angle. So you can see there the value of R that it's giving you on the calculator for the answer is equal to the supply current, which is 8.66 amps. The angle minus 29.9 degrees, which means lagging. Let's compare those two now. So if we have a look at what we did initially on the phasor diagram on the right hand side, you can see there that we had 5 amps resistive at 0 degrees. We added to that 5 amps inductive at minus 60 degrees. That gave us 8.8 amps at minus 30. Now that's solved graphically, so there's margin for error there, but it's pretty close. If you have a look at the calculation, which is going to be more accurate, we get a total current there of 8.66 amps at an angle of minus 29.9 degrees. So you can see they're very similar. And the 8.8, which is slightly higher than the actual calculated answer, is still well within tolerance when you're doing a graphical solution like that. So both of those are correct, but the calculation method is definitely more accurate than the graphical method. So hopefully that helps you understand how you can do rectangular to polar conversions, or vice versa, to solve some of those phasor diagrams that you don't like drawing. Cheers, I'll catch you later.